Okay, so great, everyone who's here. We're going to be doing this at-home experiment, and you will find, if you are watching this recording, the information needed as some extra videos, because I'm basically just going to record this part, the background on these slides. So you guys in live, you get the benefit of really getting walked through every step on the lab procedure. So what are we doing here? We are doing a process called chromatography. And chromatography is really important in separating the parts of a mixture. Okay. So it's used to separate parts in a mixture. And so we are going to be looking at the mixtures that are these colored pen inks. Okay. And so, as I mentioned, ideally you want to use some felt tip pens that the ink will dissolve in water. Okay, so the pens that don't really work well are Sharpies and highlighters and ballpoint pens. Gel ink pens also don't really work well, but they will all be fine enough if those are the only pens you have in the house. So this is not changing. Okay, try this method. All right, so when talking about a mixture is when you have substances that are basically thrown together, but they're not bonded together. So when you have a heterogeneous mixture, so heterogeneous is mixtures where you can see the parts. So this is an example of a heterogeneous mixture. All of those seeds, you can see that there's all different things in there, and you know that they're all different things, and you can see all those different things. So that's at the macroscopic level. Most things that are mixtures that we can see, like everything you have in your room right now, right? Your pens, the stuff in front of you, that's all a mixture, and none of it's bonded together. But an example of another heterogeneous mixture getting to the smaller level is when you take water and sand. You put sand in the water and the sand does not dissolve. So that is a heterogeneous mixture. Okay, but here's an example of a homogeneous mixture. Now, in a homogeneous mixture, this is one where you can't see the parts anymore. So it might be microscopic or submicroscopic, but you know that there are different parts in there. This example is if you've ever taken table salt and dissolved it in water, it looks like water. So this is a special solution. It's also a homogeneous mixture. Okay, so this is called a solution. When you have a homogeneous mixture that is a solid dissolved in water. Now we're going to be looking at a lot more of these solutions in a coming module, but that this is, you know, it's a mixture. You know the salt is in there. You originally put it in there, and you know the water's in there, but you can't see the salt anymore because it's dissolved. That's called a solution, and that's a homogeneous mixture. It's uniform. The water molecules are in there. The sodium ions and chloride ions are in there. So in this one, you know you have H2O molecules. You know you have sodium ions, that's Na+, and you also know you have Cl-. They're all uniformly mixed together and too small to see. They're all particles. They're all ions and molecules. So even with a microscope, you couldn't see all that. And so air is an example. The air that we talked about in module 2, air is a homogeneous mixture. So air, we cannot see those different gases in air. We know that the majority of air is the gas that we can't see, 78% nitrogen, or N2. Remember, nitrogen is not just N, it's always diatomic, N2. And 21% oxygen, which is not just the symbol O, it's always diatomic, or O2. So that's nitrogen and oxygen in air. And then the remaining 1% are all those other gases, the carbon dioxide gas that's leading to global warming and climate change, the air pollutants, that all the four major air pollutants, but also the minor air pollutants like the particulate matter that is worse on some days than other days, or also the random gases that are in the air because they're naturally present, like argon. And then there's water. Water vapor changes every day depending on your geography and the weather. And so those are all in the less than 1%. All the other gases that are in the mixture, and we can't see any of that, okay? And so another example is tap water. Tap water, there's a lot of different compounds in tap water. None of them is dangerous. We'll get to that in module 8. But tap water, we know, is a mixture of a lot of compounds and ions. And then the pen inks. So we can test and separate out the different components in a mixture in a chromatography experiment. Okay, so let's go to the next one. So here you've got an example of these are compounds. So how do I know this is a compound? So first of all, a compound has different elements. Different elements, when they're bonded together, is called a compound. Okay, now even though they're different elements, it's not called a mixture. A mixture is when they're not bonded together. So this is a compound because they're different elements. How do I know they're different elements? Because they're different colors. So this first one on the left has a red element and then the blue element, and they're bonded together. They're smushed together. Okay, so they're also, because they're smushed together, they're also molecules. And so that makes it a covalent compound. When the atoms are smushed together, when they no longer have their individual boundaries, they're not just spheres, they are smushed together spheres. That now you're talking about the type of bond where the atoms are sharing electrons, and so therefore their boundaries are smushed together when they're sharing those electrons. So that's called a molecule. But it's also a compound because they're different elements bonded together. This is a compound as well, this other box. Why? Because they're different elements. And you know that because they're different colors. You've got the white atoms and you've got the black atoms. They're also smushed together. So they also can be defined as molecules. Okay, and so that also would be a covalent compound. And a covalent compound, in a quick reminder from last week, are when you have two non-metals bonded together. That's different from an ionic compound. The ionic compound, which has the whole process for writing names of ionic compounds with the crossover rule, determining ions using the periodic table. Ionic compounds are more complex in naming, and the atoms are not smushed together. So they do appear as individual spheres when the ions come together, okay? So this is a mixture, is when you have the different elements and they're not bonded together. So you know that they're different elements because they're different colors. So you have different elements here. You also have a molecule. That's a compound where those elements have been bonded together. That's this one. Okay, but this is one type of element because it's identified by red. This is a different element, that purple color, because it's a different element, different color. And then you have, this is a molecule where those two elements have bonded together. When all of these are not bonded together, that makes it a mixture. Okay, so when you have a whole bunch of different things thrown together, that's going to be a mixture. Now we can't decide if it's heterogeneous or homogeneous when you're given the molecular view. So the definition of a heterogeneous mixture is really when you're not given a molecular view, when you're given a picture and you can see the different parts, okay? So this is just a mixture in general. Okay, so chromatography is important because it is used to separate a mixture. And it's a very common laboratory technique. It is used to separate environmental samples, like talking about these air pollutants. So this would be an example of when you're testing your regular air, you can find out how much of an air pollutant is in there. So how much is the air pollutant, which is really important in keeping our air fresh, how much of one air pollutant is present? So when you're trying to figure out how much of one of the parts in the mixture, that's when you're going to use chromatography. Another thing that chromatography is used for is isolating new compounds in drugs. If you're going to work at a drug company, even not as a laboratory tech person like her or a researcher, you might be part of human resources, or you might be part of the marketing campaign of a new drug. Well, you can understand a little bit about part of the process if you've taken Chem 9, which is very important in determining new drugs. Is once you make your drug, usually you have to separate it. So this is a column. This is called column chromatography, and it is used to separate some compounds that are made in a mixture. And then you have the one thing, the one drug that you made, and you want to separate it out and just study that one drug. It's used to separate proteins of different sizes. It's used in food industry. Let's say you have something that you make, your new type of soda, but then there's some compounds in there you don't want. Well, you got to separate out the stuff you don't want and the new soda that you did make. So here's a human example. Oh, actually, no. Don't want to go there yet. Okay. So when you are separating components of colored inks, this is the process using chromatography paper. So the chromatography paper is what's called the stationary phase. The stationary phase has to be a solid or a semi-solid. Okay. It doesn't move. Stationary phase. Okay. And this solid or semi-solid is where you apply the samples to. So in this example, this is a chromatography paper. Whoops, my hand just made all that move. This is a chromatography paper. And down here are the different colors, are the different samples. Okay, so these are the different samples, and they're applied at the bottom. And you guys are going to be doing something very similar. Okay, so instead of having one big piece of chromatography paper, you have individual strips. But the chromatography paper, that is the stationary phase. Hopefully you got that in the pre-lab. It is a solid or semi-solid, and so it can be paper, it can be that gel column I showed you in the previous. And what is important is that it doesn't move, and it's what you apply the samples onto. So the samples are these gel ink samples. So these ink samples, these colored ink samples. Okay, so the samples go onto the paper. And so here there's 1, 2, 3 samples that are on there that you can see. Okay, so then you need to have a mobile phase. The mobile phase does move. And how does it move? It's because in this mobile phase that you're going to use in today's lab is water. And it can move because it is a liquid or a gas. So remember, in the water lab, we looked at the differences at the molecular level of solids, liquids, and gases. Solids are all tightly packed together and not moving. Liquids and gases are molecules that are moving. And so the water, as the mobile phase, the molecules are moving, they're bouncing around. And what those molecules do is these molecules, the water molecules, is going to be absorbed. And this is what we know as capillary action. Capillary action that we saw in the water lab. It causes the water to move, and it moves up the paper against gravity. So just like the experiment you guys did where you got water to move from one cup to the other through a paper towel. Well, what water does is it moves up this chromatography paper, up the stationary phase against gravity because of capillary action. So the water moves up, and as the water moves up, it causes a separation of those inks. And that's the goal, is to separate those components. Okay, so now how does that work? So here's an example, a human example thinking about this is, let's say you have a room with 5 people in a room. Okay, so picture yourself and 4 of your friends sitting in your room. Okay, So you plus four people. That's 5 people in a room. Okay. So now me jumps out of my Zoom. I jump out of my Zoom. I miraculously end up in your room in that with those 5 people and say, hey, who wants to come with me and go outside and walk around the block? That's me, right? So I go in there and I talk to all 5 of you and I say, who wants to come with me and leave this room and go outside? So one person might take me up on that. That might be you because you're in my class. And you're like, hey, I'll do that. And so you go outside with me. The other 4 stay in the room. Okay. So that, what I just gave you is an example of the stationary phase. The stationary phase is that room. The samples are in that room. The people are in that room and they're stuck there. But then the mobile phase is something that makes that stuff move. What's a mobile phase? That was me. I'm the person, I come in, I jump in, I grab someone and say, let's go. The difference is only one person went with me. So separating out the 5 people, they're not all going to decide to go with me. Not all components. So some components, let me put it this way. Some components are going to be more attracted to the mobile phase. And so when there are components that are attracted to the mobile phase, they will move with the water. So in my human example, you, out of the 5 who decide to come with me, you are more attracted to the moving, the me, the I said, hey, who wants to go with me outside? So you were attracted to the mobile phase and you went outside. Other components, all the rest of them are going to be more attracted to the stationary phase. And what does that mean when they're more attracted to the stationary phase? They're not going to move. They're going to stay and they're not going to move. You will also have all the possibilities that are in between. So back to this example, when these inks move, and I'll show you this video of it, is that they some inks will move fast and they'll go right with the line of the water. They'll move right at the very edge of the water as the water moves. Some inks won't move as fast and they'll stay back, okay? And so then you'll have a whole range of movement in between. Some inks will move halfway up. Some inks will move a third of the way up. And so that's all some differential based on between the attraction to the mobile phase or an attraction to the stationary phase or something a little bit of both. So back to the human example, I had 5 people in the room. When I came along, one of them came with me. Well, then the other 4, another one waited around for 5 minutes and then decided to come outside and find us. The other 3, another one decided to wait around for 10 minutes and then decided to come out with me. And so the other 2 just stayed. All right, so there's a difference you can have of all the different components in a mixture, and that will play out in the separation. So let me show you, this is the video of what happens when you have a chromatography, what's called the elution process. So remember, I put the inks on here. They were originally samples applied at the very bottom. And as the water moves up, it causes the ink colors to separate. So let's show you what happens. This is sped up. So the water is moving up and the inks move up. And what is going on is that you see a separation of colors. You notice here for this one, that this started off a purple ink color. And this separates where this is a blue. The blue is more attracted. It's moving with the water. So this blue is more attracted to the mobile phase. How do I know that? Because it is traveling with the water right at the front edge of the water. And this compares to, this is yellow. The yellow ink is more attracted to the stationary phase. Why do I know that? Because it is basically staying put. It is staying put and it's kind of lagging behind, okay? So you can see that it doesn't just move as a little dot, it moves and kind of spreads out. It's like kind of thinking, I'm gonna move, but I'm gonna stay back a little bit. And so here's an example of green. So green also is attracted to the mobile phase and it's moving with the front of it, okay? It's moving with the water and this is the level of the water right there. Okay, how do you guys feel about that? So let's take a look at, this is going to here, part A. So let's get started on the experiment. So in part A, you have your 6 chromatography paper strips and you can do 6, you can do 8, you can do 50, but you need a minimum of 6 for the experiment. So get your 6 chromatography paper strips, your colored inks, and your ruler. You're also going to need a ruler. I need to add this on here. You need a ruler. You also need a pencil in getting these prepped. Okay. And so you can see I've got some different ink colors. I've got my paper strips. So go get those because I'm going to walk you through this lab procedure one step at a time. So this is where you're jumping into action. Okay. So I'm going to take one strip right now off. And I'm going to do one strip at a time, even though I have all 6 ready to go. Okay, so I've got one strip right here. Okay, so you need that ruler to take some measurements. And so the ruler you're going to use on that strip of paper, and you're going to hold that paper in the horizontal position. So horizontal where it's long across. And then your ruler is gonna, from the 0 mark. So notice where this 0 mark meets. This is the 0 mark, not the edge of the ruler. And you wanna line up the 0 mark with the edge of your paper. And then from that edge of the 0 mark, this is 0, you wanna measure 1.5 centimeters. So 1.5 centimeters and then make a line across. You don't have to write the 1.5 centimeters. So here's what I'm going to do. And then you also want to make another mark that's 8.5. So at the same time, you want to make 2 marks on your paper, 1.5 and 8.5. So I'll show you this on my live camera. So I've got this 0 mark. And then I'm making a mark at 1.5. It doesn't have to be exact, but all you have to do is write a line straight across. Okay. And then let me turn this so that it's not upside down.
Professor?
Yes.
Do you want us doing this to all 6 strips of chromatography paper?
Yes.
Or just the first one? Okay.
Yes, all 6.
Thank you.
So this is, you might as well do all 6 while I'm trying to figure out which way is up. Okay, let me pause this. So make sure you use pencil for these marks. The next thing you want to do is take one strip. So for one strip, and you want to do this one strip at a time, you want to first take that strip and wrap it around a pencil. So wrap it around a pencil with the top part. So this was the bottom. The bottom part is this where the 1.5, this lower mark, and the top part is the 8.5. You want to take the top part, that's the majority of the strip, and wrap it around a pencil, and then either affix it using tape or a binder clip. So you can use tape if you don't have a binder clip, okay? You can use tape or the binder clip, okay? So this, you want to check now. So you have to have 1 cup, and you have to have 1 cup that is where you're going to run the experiment in. It doesn't have to be a clear cup, but here's my cup. And so you want to check the length of that chromatography strip in that cup. So basically the strip should not touch the bottom or the sides of the cup. Okay, so you want that strip to hang down and it should not touch the bottom of the cup or the sides. And it should be straight up and down. It shouldn't be at an angle. So you might need to adjust your clip. You might need to find a pencil that's not round. And you might even need to hold it so that it hangs straight down. Okay, so that is going to be testing just one of them. So I've got my one here, and you want to then take it out. Okay, so test it, make sure it's all set, and you are going to do that one at a time. Now, if you decide to set up all 6, you're going to need 6 strips, 6 binder clips, 6 pencils, 6 cups. That's okay too. But I'm just showing you the example one at a time. Okay.
So we need to wrap it around the pencil, the top of the paper.
Yes.
Okay.
Mm-hmm. Looks like this. And the reason why you're wrapping it around the top is because if you don't wrap it around the top, it's going to be too long coming down to the bottom of the cup. You want to make sure it doesn't touch the bottom of the cup. Okay, so wrap it around. I'm going to show you actually using some tape. I'm going to use some tape on this one. It doesn't have to be tight. It just has to be, what's most important is that the paper doesn't touch the sides or the bottom of the cup when you test it. Tape actually works really well. Okay, so in the next one, so that's a test, and then you want to take it out. Okay, so remove that pencil with and keep it all attached. Remove it from the cup, but don't dismantle it. Now you're going to apply a sample of ink. Okay, so that's on the starting line. The starting line is that bottom starting line. Whoops, go back. Okay, so the starting line is that bottom starting line, that 1.5. You want to add a dot of your ink color. And it is going to be a dot. It doesn't have to be exact. I put about 0.1 centimeters, but you're putting a dot, not a small dot, not a big dot, but a dot about 0.1 centimeters, or just whatever dot you have that seems like a dot to you. So I'm showing this on my screen. You want to make sure that it is a dot that could also, if it does not have to be too big, but it might be too small. So you don't want it to be too small. You could also do a line straight across. I'm going to do a line straight across on this one. So a dot or a line straight across.
And that's at the one.
Okay. So at the top of that strip where you have the pencil and it's still stuck together, you want to write the name of that ink color, whatever it was. If it was black, red, yellow, and you want to, don't use the pen, use the pencil. Why? Because if you use the pen, it's going to run on the chromatography paper strip. So use a pencil to write the name of that ink color. Okay. And that's going to identify that original ink color because these are all going to separate. So you can write a dot, and this video I think shows a line. Let me see. I don't think the video is working on here. No, I don't have the video there. All right, that's fine. We can do it without the video. So you have this all set right now. You have a piece of paper with one line or a dot with a dot at the bottom, and this is all stuck to the pencil. Set that aside. Now you want to measure some water. So you can use your beaker or you can use a tablespoon. You want about 2 tablespoons of water. Go get your cup and set it wherever you're going to do your experiment. Okay, now this is important. Wherever you're going to do your experiment is where you're going to set that cup and don't move it. Okay, so this is, I'm going to set my cup up right now. I'm trying to find this so it's not upside down. Okay, so you want this cup to have its water and then be nice and settled. So this is my cup. I'm going to show you this cup. Okay, is this all upside down? Oh gosh. You need to set that cup wherever it's going to be running the experiment. So not in your kitchen, not in your bedroom, wherever you're going to run this experiment for the next, approximately hour or 15 minutes at a time. It takes about 10 to 15 minutes per strip. You don't want to move that cup while this experiment is running. So the water needs to settle out. And you have now the experiment can go once the water's settled out, once the cup is set. Ideally, when you put this strip of paper in, this the dot of color will be above the water line. Okay, and so if you've measured the water correctly, it's either 2 tablespoons or 30 milliliters. Once you're ready to put this paper in, and I'm going to show you, I'm going to put this paper in right now. Ooh, I just did not record all of that. So you're waiting for the water to get up the paper and about 1/2 centimeter below the finish line. And once it gets to about that point, about 1/2 centimeter below the finish line, the water will continue to travel up even after you've taken this paper out. And then it'll probably get to about that finish line. So you can see what I've done is I've put in 3 strips in the 1 cup. The strips should not touch the bottom. They should not touch each other. They should not touch the sides of the cup. The strips need to hang straight down. And you also need to keep an eye on the water level. You want to make sure the water level, you want to catch it right before it hits that finish line, which is that top line you had drawn at 8.5. And so it's right before it hits the finish line is what you're looking for. And if, for example, you take it out before the finish line, that's okay too. So this is an example that I took one out. It is before this is at the finish line, and you want to take it out and dry it. It's going to, the water will continue to travel even after you've taken the paper out of the water. And so what's going to be important is let the water travel a little bit more, until it starts to dry off. And you want to mark where the water traveled to. Okay, so the actual finish line. So let me show you this on here. Is the actual finish line will not be the same. Or the actual water line is what you need to mark. Mark the actual water line, and it will probably be different, or probably won't be the same. Let me actually try to write this. Okay, so your water line, your actual water line, will probably be different from that finish line. And that's the finish line you originally marked. The finish line is just a goal. That's a goal so that you have an idea of when this experiment is going to end, when you should pull this paper out. Okay, but the idea is that you are going to pull this out at some point. So I'll show you mine in a second. That my first paper I took out a little bit early, and that's okay. If you take this out early, that's okay. You just need to mark the actual water line, how far it got to. It might be a little bit low or it might be high. And the reason why it might be above is because the water will continue to travel. The water will keep traveling up even after you take it out. Okay, so I'm waiting for this actually to keep traveling. It travels for another 5 minutes or so before it starts to dry out. And that also depends on the humidity in your own home. So I'm going to, on here, show you the actual water lines. Okay, so this is the actual water line that you need to mark, or the actual water line for all of these. You need to mark the actual water line. And you can see for these, the examples, all of these examples, the actual water line is not the same as the finish line that I had originally marked, that you can see those pencil marks. Okay, so, and this actual water line is above here. And this actually is a marking that was a little bit short. So what I mean by a little bit short is that this this distance here was not 1.5 and 8.5. For whatever reason, the second distance was way less than 8.5. Okay. But the actual water lines, those are marked in red. These guys, 1, 2, 3, 4, 5, 6. These guys, 1, 2, 3, 4, 5, 6. The actual water line is not the same as the original finish line that you originally marked, and that is okay. Okay. Yes, this is really working. Hold on a second. Sorry, I did not have this on the screen when I was talking. Your actual water line, which are these red lines, that actual water line is not the same for every one of my strips. The finish line is lower. And that's because basically when I did these experiments, I waited until the water hit the finish line. And you can see what happens is the water it travels a little bit after you take it out. So that's why you can wait until it hits the finish line, or you can try to take it out a little bit early and then mark it how far the water got to. Okay, but you will take a picture of all 6 when they're done.